Hey everybody, Bill Sky, the assembly guy, back again, and this time another lecture video, and this is on 2's complement. Now we're going to jump over to Linux and we're going to take a look at the binary representation of data so you can actually see what 2's complement is. We're even going to do a little bit of programming where we add some numbers together, which is kind of like the day after you do the Hello World program. So let's get started on this discussion. Now, 2's complement is how numbers are stored in the computer, and signed numbers to be specific, and that includes memory or the registers, which we're very close to talking about. And the registers are the hard-coded variables inside of the CPU. Now, remember when talking about signed numbers in our binary number system, we talked about this in the video, is that the most significant bit is actually used to keep track of whether or not a number is signed or not. So if you remember, if we had a number that looked something like this, and we're only talking about a nibble here, we're only talking about 4 bits, what is the sign of this number? Well, if you're looking at it as a signed number, this guy right here, the most significant bit, which is a 1, says it's signed. So what about unsigned? Remember in the video we talked about an unsigned number, the most significant bit would be a 0. So that's unsigned. So, but that's not the end of the story. That's absolutely not the end of the story. You still need to, or the CPU still does things in such a way to make it more efficient for the architecture of the CPU to do arithmetic. So not only is the MSB, the most significant bit, indicate whether or not the number is signed or not, but it also, the rest of the bits also are changed to 2's complement format. So I've said that many times. So what is 2's complement? 2's complement is the process of changing the bits in a value to make it easier for the CPU to do signed arithmetic on the number. And any negative number is stored in 2's complement in memory or in the CPU registers itself. Now if it's a positive number, there's no need for 2's complement. But when it comes to negative numbers, there is. So what do we actually do to implement 2's complement? And it's a very simple procedure. So to convert a positive number, or positive integer, into a negative integer, there's a predefined process to do this conversion. It's simple, a little bit weird, but this is how it works, and then we're going to demonstrate it in some code. So the procedure is simple. To convert positive 1 to negative 1, we flip all of the bits, so all zeros become 1s and all 1s become 0s, and then we add 1 to the number in its entirety. That's it. To go from a negative 1 to a positive 1, we do the exact same thing. So here's an example right here where we've got a positive 1 binary, 2 nibbles. We flip all the bits, so we get all the zeros to 1s and all the 1s to 0s, and then we add 1. That, believe it or not, is a negative 1. Now, how can you prove this? Well, it's very simple. Just go ahead and take those all 1 bits in step number 1 here. Take them all. That's a negative 1, if you remember our previous screen. Now add 1 to that, and what do you get? You get all zeros. There is a carry bit that's lobbed off the end of the most significant bit as you move left, but it's now all zeros. So negative 1 plus 1 is 0. There you go, right there. So to convert a negative number back to positive, you use the exact same procedure. You flip all the bits, and then you add 1 to the number. You could subtract 1 from the number and then flip all the bits, but it produces the exact same result. So let's go ahead and take a look at this in actual code. So you guys are going to be able to see this, and then that's all we're going to do on this video. That's the procedure. So let's get to the demo. All right, the demo. Let's take a look at this. So I'm going to jump over here to my documents folder. I'm going to create, let's just do a 32-bit one. I'm just going to go ahead and right click on that, extract here, and let's rename it. See, this is the problem if you don't rename your projects, your folders after you create them, is you get the same thing over and over again. You don't know what it is. So I'm going to go ahead and rename this. So let's call this 2's complement x86. Linux. All right, cool. And let's go ahead and edit it. All right, so in the data section, let's go ahead and create a negative number. So I'm going to say negative D word, define double, and I'm going to make it a -1. That's all we're going to do on the data section. That's our variable. Then what I'm going to do is I'm going to add 1 to that -1, and it should turn out to be 0. So some new coding here. So what we're going to do is we're going to move negative D word, and actually I did that wrong. We're going to move into EAX negative D word. Now EAX is a CPU register, and when you do arithmetic in the program, you pretty much always want to do it within the CPU. So what we're doing here is we're taking the contents of neg D word, and notice the square brackets around it. That means go get the data. If we don't have those square brackets, it just puts the memory address of negative D word into EAX. So by putting the square brackets around it, we're dereferencing it like a pointer in C++ or in C, and we're putting that value into EAX. And then I'm going to subtract, or no, we were going to add, right? I'm going to add, because negative D word has 1 byte, -1, and actually 4 bytes, -1. We're going to add EAX 1 value. So we're going to add 1 to EAX. Now what we're going to do in the debugger is we're going to take a look at EAX while this is running. Let's go ahead and just say subtract EAX, 1, and we'll see it go back into 2's complement. All right, so let's go ahead and make it. Okay, looks good. Let's go ahead and debug it now. All right, KDBG, great little debugger. So let's make this a little bit bigger. All right, so we're going to put a breakpoint on the first no-op in my text section, which is where our code is located. And all of our data variables, all of our arrays, anything we produce is in the data or the BSS section. And we'll talk about the BSX section soon. So let's click the Run button. And what I'm going to do is I'm going to look at registers. So I'm going to click on registers. In the past, we've always clicked on memory. I'm going to click on registers this time. And now I'm going to press the step over button. Now, I don't believe we've ever done this. So step over means execute the line of code and move on to the next. And what we're going to do is we're going to be watching that EAX register. So let's step over. So now we're going to move the negative D word, dereference square brackets, into EAX. And here you go. So we've got the EAX register, which is one of the general purpose registers of the CPU. We have EAX, all Fs. It's 4 bytes. We've got 8 Fs there, 8 nibbles. And that's as we showed in our demonstration or in our lecture before this demo. And KDBG is a great little debugger. It shows the decoded value. So it shows it as a -1. So now the next line of code, 21, we're going to add 1 to EAX. Let's keep an eye out on EAX down here. Step over. And it's now 0. So -1 plus 1 is now 0. It's now no longer in 2's complement. It's now 0. Let's go ahead and step over again. It's now -1 again because we subtracted 1 from EAX. So we went 0 minus 1. Now, I would have loved to have done this. Actually, we could have done this in Windows, no problem. Okay, one last thing I wanted to mention is remember that the CPU, as far as the CPU is concerned, it doesn't know anything about signed or unsigned. You as the programmer have to keep track of that. If something is could possibly become negative, that means that it must be a signed number. If it's always going to be positive, it doesn't have to be a signed number. So I always like to add a little s or something like that to my variable names if I intend on those ever being negative, and then I just put the s there if they're always going to be positive. So just a little hint. We'll get more experience on this as the course moves on. So that's it. 2's complement. Not too long of a video. See you at the next one.